In this mini R lesson, we're going to walk through the process of evaluating whether a variable is normally distributed or not. So to orient you here, I have an R project that has my code up here on the top left, and that's going to give us access to, or we're going to use that to access the data set that's here in the same folder as the code. So step one is actually to install these first couple of lines here, or use these first couple of lines to install our packages that we might need for this project. So that gives us ggplot and PSYCO, so we're all set up there. Next, we're going to use the read.csv function here to import our data. Now, because our data set is in the same folder as where the R code is that I'm using here, we don't have to specify anything other than the file name when we're telling it to read, so that's a convenient setup. I've also made it so that this is our directory, which you can set under this button here. So you set as a working directory, and that makes sure that you're actually going to be pulling from this particular folder, which I had to learn the hard way earlier. So we've set that up, we've imported that data, so it tells us that we already have that W data, that's what we've called it. It gives us 30 observations of one variable. In this case, that variable is IQ. And that's to match the example that we used from class. So if you recall, we're using IQ because it has a score that has an expected population average and distribution. So specifically, when IQ tests are created and normed, they're adjusted to have an expected average of 100. And then we also had that predicted standard deviation, which isn't as important here. So this is a meaningful population value that we can then test against, rather than comparing between two or more groups, which we'll be doing in later weeks in the course. So for here, what we've got is the IQ scores for 30 different individuals. The next few lines in the code here give us the descriptive statistics. So I'm using the function that they have in the PSYCO package, and we can run that to get our descriptive statistics of our IQ scores. And then if we look at the bottom here, it shows that our mean is 109.7. It gives us a standard deviation, a median, and all these other things. But that's sort of more than what we need for right now. What we're actually here to look at is what helps us decide if this is normally distributed data. So what are we going to look at? And if you've looked at the notes on our code here, you've probably figured out that we're interested in looking at the skewness and the kurtosis. So we see that we have a skew of minus 0.7 and a kurtosis of minus 0.33, but is that good? Is that bad? How do we actually evaluate those? We also, at this point, want to keep in mind that we're working with real data. And when we work with real data, our values are never going to be perfectly normal. So you're always going to expect a little bit of deviation from normal, but how different is too different? So in these cases, it's actually a lot easier to visually inspect the data. So as opposed to trying to interpret these skew and kurtosis values, we're actually going to look at some graphs here. So if we can visualize what we want to look at, we can run this first section here. And this is using ggplot in order to create a histogram of our IQ score. So that's what's popped up over here. So we have density on our y-axis, which is a little bit different than what we've been using so far. But for what we're using it for here, we're basically calling density equivalent to frequency because that's basically what we're seeing here. So in the code, we specified that we have a bin width of 5. So that's how wide these bars are. You don't actually have to specify a bin width. It would pick an appropriate bin width on its own, but if you're picky about the width, then this is how you would change it. So let's actually look at the graph. How does our distribution look? As we might have expected from those descriptive statistics, we are actually seeing a little bit of a negative skew here. So it's not necessarily symmetrical about the middle. We're seeing a little bit of a tail off on this negative side. What we can do to actually help us visualize this is run the whole chunk here, which will also allow us to superimpose a normal curve with the mean and standard deviation of our data on top of this graph. So we can see how our data compares to how similar but normally distributed data would look. And we'll notice that they're sort of not meeting up to the line on this side, and we're protruding over the line on that side, and then there's too much down here. So we're a little bit off from a normal curve. Another way to look at the same data here is that you can actually run a data plot, or a density curve. And to do that, we would just highlight the next chunk of code and tell that to run. And we've set it up again so that the black curve here is our data, and then the red is a normal distribution that we would expect if our data were normal. Now, this is basically the same information that we just saw in the histogram, but in this case, this density plot includes a little bit of smoothing, so it's not as jagged as what we saw in our histogram, and that smoothing can actually make it a little bit less intuitive to interpret in some cases, so a lot of times you'll just end up going with the histogram, and that's totally fine. Another useful technique might actually be creating a box plot. So if we run our next little chunk here, we can run that, and we get a different visualization of our information here. In this case, this center line is actually our median. So that's the middle of our data. And this box is going to enclose the middle 50% of our data. So the lower is that 25th percentile, and the upper is the 75th percentile. So in between here, there's 50, or from the 25th percentile to the middle. You can also call it the 50th percentile if that's easier. That's 25% of our data points fall between those points, and then between the middle and our 75th percentile, that's another 25% of our data. So that's a full 50% between these two vertical points. And then if we look at these little lines that stick out above and below, that's showing us the range of our data. So this would be our lowest data point, and this would be our highest data point. And if we had any extreme outliers, they would show up not on this line, but as a separate standalone little dot. So that's just how we look at this here. While we're at this point, we could take a look here and notice that our median falls right around that 112 point. So, but if we look back at our descriptive statistics here, so the median's 112, our mean was only 109. So we actually have a pretty big difference where our mean is further to the left there. And if you think back to what our mean, median, and mode all do as we have skewed data, that kind of actually makes sense, because the median tends to be fairly resilient in not being affected by skew, but the mean, getting the average of the data, can be pulled in the direction of outliers of that tail that trails off when you have either a positive or negative skew. So in this case, a negative skew means that our mean is closer to that negative side than our median is. It's been pulled to that one side. Now, we've saved what is arguably the most useful function for this purpose for our last thing to run. So if we run our last chunk here, we get this graph. So you may have seen these before, you may not, but this is a quantile plot, which is also called a QQ plot. And so in order to set this up, basically you would rank order all of your data from lowest to highest, do the same for some theoretical data that follows the normal distribution that we saw in our earlier examples. So the same average as our data, but normally distributed. And then we graph those two ordered sets against each other. That gives you this QQ plot. So these dots are showing how our data compares to that theoretically normal data that's close to ours. And ideally, if our data were perfectly normal, all of these dots would line up along this line, this diagonal down the middle. However, as we see, we deviate from that middle line quite a bit, especially at the ends. And so that's a good sign that our data is non-normal and specifically skewed. So we'll start to be able to recognize QQ plots of comparatively skewed data. Now, the last thing that I want to show you is actually running a statistical test of normality, and this is the Shapiro-Wilkes test. So that's this one down at the bottom here. So we can tell that to run, and it's going to print out this at the bottom. So it's a Shapiro-Wilkes normality test. And what we care about in this situation is the p-value. So a lower p-value for this test tells us that we have a larger deviation from normality. So we have a p-value of 0.07. So what can we conclude? In this case, we're actually kind of borderline. Since we're not at that p of 0.05, which is the magical number for significance, we could write this up and say that this has passed the Shapiro-Wilkes test for normality. But from looking at our data, we did see quite a bit of deviation from normality. So what do we do? And if we think about it, what's probably going on is that because our sample size is very small, this test isn't very sensitive at detecting deviations from normality. And in fact, you can actually have the opposite issue if you had a very large sample size. So if you had something like the IQ scores for 2,000 students or whatever, the data might look perfectly normal from all of the plots that we already looked at, but this Shapiro-Wilkes test might come back as significant because it ends up actually being too sensitive with larger sample sizes, which is really annoying. And because of this, not sensitive enough at small and too sensitive at larger, sometimes it's actually easier and better to just use the plots and a visual investigation to determine if your data is normal or not. And that's going to be sort of the most reliable method to choose, but it might depend on what kind of research you're doing and what the convention is for that field. But that's our rundown for testing normality.